Here we have a particle, well, it's a book being modelled by a particle with a mass of 8 newtons, with a weight of 8 newtons. So if I just put that in as acting vertically downwards, there's the weight, and that has a magnitude of 8 newtons. So the other forces that are acting here, we've also got the normal reaction, which is acting at right angles to the slope. I don't know what that is at the moment, so I'm just going to call it R. And as there are no other forces acting, it must be the case that the frictional force is acting up the slope. Because if that frictional force wasn't there, then the book would go sliding down the slope. Now, we don't know whether it's in limiting equilibrium, so I'm just going to call the frictional force F. And I don't know whether it's limiting or not, so I'm just going to leave it at that for now. Okay, we're told that the slope is making an angle of 28 degrees with the horizontal, so I'm just going to put some angles in here. I know that that's 28, which means that this angle up here must be 62 degrees, because there we have a right angle. And I'm just going to put in the imaginary line here, so that the angle that's made here with the imaginary line there must be another 28 degrees. And if I just put in another horizontal line, then this must be 62 degrees here, and this has got to be 28 degrees. Now I know that the particle is in equilibrium, and because it's in equilibrium, that means that the forces which are tending to make it move up the slope are going to exactly equal the forces which are making it move down the slope. There's no movement up the slope or down the slope. Acting up the slope, we've got F. And acting against F, in other words, acting in this direction, we've got the component of the weight which acts in this direction. In other words, it's going to be 8 times the cosine of this angle. In other words, 8 cos 62 degrees. So the frictional force must be 8 cos 62 degrees, and that comes out as 3.7557 newtons, which I can just round to 3.76 newtons. The question then says that the coefficient of friction between the book and the slope is 0.6. And we need to work out whether the book is in limiting equilibrium. Now, if it's in limiting equilibrium, that means that this frictional force has to be at its maximum. So what I'm going to do is I'm going to find out the maximum possible frictional force which is acting. And I know that that is equal to mu r. Now I know what mu is, I'm just told that's 0.6. My job then is to find out what r is. And I'm going to use the fact that the particle is in equilibrium. In other words, the forces which are tending to make it move away from the slope are exactly equal to the forces which are tending to make it move towards the slope. Acting away from the slope then is just r, no other forces acting. F I can ignore because I'm looking in this direction and F is at right angles to that, but r must equal the component of the weight which is acting in this direction, and that's going to be 8 cos 28 degrees. So my r is 8 cos 28 degrees, which means that F max is going to be mu r, so 0.6 multiplied by 8 cos 28 degrees. And if I work that out, it comes out as 4.238 newtons. So the maximum possible frictional force is 4.238 newtons. And what I've established up here is that the actual frictional force which is acting is only 3.76 newtons, which is less than the maximum possible frictional force. In other words, the frictional force is not at a maximum, so we haven't got limiting equilibrium. So because the frictional force is less than the maximum possible frictional force, we have not got limiting equilibrium, because if we did have limiting equilibrium, the frictional force would be at its maximum.